I am happy to welcome up next. We have Brian Hogan, and Brian's going to be talking about building resilient applications with Poly. So,
Hello. Hey, John.
Take it away, Brian.
Thank you very much. As John said, my name is Brian Hogan. I have been using Poly for quite a few years and writing about it and occasionally presenting. And today, I'm going to give you a quick overview of the whole lot of the resilience framework. Failures happen. They can happen anytime to any application, and they will happen to your application. What do we do about it when something goes wrong? Many of us work on applications that rely on connectivity, but connectivity has never, ever been a guarantee. We have to deal with software failures, local network outages, and of course, an unreliable internet. Any problem along the way, and it could lead to your request failing. For applications such as mobile applications or IoT or embedded systems, this is especially true. So what will your application do if there's a transient fault or a longer outage when making a request to a remote system? Will the whole thing grind to a halt, or will you lose just that one request? For a lot of applications, losing a single request might be fine. But for critical applications, think of medical, financial, losing a single request can be quite serious. What could you do about it? The obvious answer is to retry a request. So think of your local system making requests to remote systems. Make a request, get back a failure. Retry it, get back a failure. Retry, failure, retry, success. So keep retrying until you get a response. Keep retrying within reason, not forever, of course. So how might you program up something like that? If you're using HTTP client, you'll have a get async hitting a remote endpoint. You might put a for loop around it, which specifies the number of times to retry. You'd have a catch looking for exceptions. And then you might have a break to get out of that loop when you have a success. I've had people at conferences tell me that this is a fine approach, but from my perspective, it's fragile, be very hard to use in multiple locations, hard to change, hard to configure, hard to customize. And of course, we're here to talk about Poly. Poly is a resilience framework for .NET, and if you're working in Microsoft, as I imagine most of us are, it's really the only game in town. If you have worked in Java, you've probably come across Hystrix. Poly helps protect your application from failure, but it has a knock-on effect on upstream and downstream applications, helping them to remain stable also. With Poly, you can handle all sorts of failures. Poly helps you to do this through what are called policies, such as Retry, Wait and Retry, Circuit Breaker, and a few more. Poly was started in 2013 by Michael Wolfenden, but more recently it was taken over by the AppV Next group with Dylan Reisenberger as the lead architect on the project. Poly is active on GitHub, Slack, they have a blog, and it's getting about 150,000 downloads per day. Dylan has been on my podcast and on .NET Rocks. Over the last few years, the popularity of Poly has soared. When I started working on Poly, it was something like, I remember 10 to 14,000 downloads per day. Those are the numbers I remember, and now it's at 150. As I said a moment ago, Poly works on all .NET platforms. So again, think of how this might help you with mobile applications, embedded devices, or IoT, where connections are more tricky. For those of us who may be working on technology that's pre-.NET Core 2.1 or .NET 5, our request with Poly would look something like this. You have your HTTP GET, and it's wrapped inside a policy. The policy is defined like this, where you say it handles a HTTP response message looking for a success code. If you don't get one, or if you get an exception, you should perform a retry. That's pretty good, relatively easy. But since .NET Core 2.1, this is all you need at the point of execution. There's no sign of Poly, there's no sign of the policies. It is your familiar and traditional HTTP GET, and you get a HTTP response. You don't have to unwrap it. You don't have to do anything with it. You don't need to pass the policies around. This is thanks to the HttpClientFactory, and I'm going to talk about that a little bit more in a few minutes. When I started working with Poly, and when I started working on a Pluralsight course for it, I looked to see if there was any definition out there of a resilience framework, and there wasn't, so I came up with my own. From my perspective, a resilience framework actively protects resources, restricting the amount of memory, threads, and sockets that an application can use. When possible, it will let you recover from a failure through something like a retry, and if recovery is not possible, it will facilitate graceful degradation. Now, what graceful degradation is very much up to you. It might mean that you fail quickly rather than slowly, or that you reduce load on remote systems, or potentially shed load on your own application. And again, all of these have a knock-on effect of helping the services that you depend on also, by not overloading them if they're stressed, giving them a break, giving them a chance to recover. At the heart of Poly are policies. These are things such as a retry, timeout, and circuit breaker, and I will get to each one of those in turn. A policy is made up of two parts, two clauses, let's say, the handles clause and the behavior clause. The handles clause specifies the failure the policy should respond to, like a 400, 401, or some type of exception. And the behavior clause specifies what should be done. In this case, retry 3 times. As you can see here in a fluent style, they're reusable. A single policy can be used in multiple places and will not interfere with another use of that same policy. They're thread safe. It is no problem at all to use the same policy at the same time in multiple places. Each policy can execute a delegate to perform an action before the behavior clause kicks in. So think of the example of a reauthorization. There's not much point in retrying a request that failed due to reauthorization unless you do something to fix that authorization issue. And I'll show you that as well in a sec. Poly supports synchronous and asynchronous requests. And finally, you can wrap policies. So the idea would be you'd have a HTTP request with a retry policy around it, with another one like a circuit breaker around that, and then potentially a fallback around everything. Poly policies are broken into 2 broad categories: the reactive strategies and the proactive strategies. The reactive strategies are made up of the retry, wait and retry, circuit breaker, and fallback. These respond to problems that have happened. Proactive strategies monitor ongoing events and attempt to prevent problems from occurring, and they stabilize the system or potentially allow you to fail gracefully. And the proactive policies are timeout, caching, and bulkhead isolation. And I will go through each one of those in turn. To give you an idea of where Poly sits and how it works when it's interacting with a request, I'm going to go through the example of a retry policy. You make a request, Poly checks if it was a success. If it wasn't, Poly checks whether or not it should perform a retry. If it should perform the retry, it will make that request again. Poly will then check again if it was a success. If it was, it will return you the response, the HTTP response that you would normally expect. If it was not a success, it will check again whether or not it should retry. And if it should not retry at this point, you've, let's say, used up all the retries that you were going to make, it will return a response, which will be, again, a HTTP response indicating failure. Poly doesn't interfere with the flow of the request. If it succeeds, Poly doesn't do anything. If the request fails and should not be retried, Poly doesn't do anything. With a retry policy, you can make hundreds of requests using a single policy, and they will not interfere with each other. Making a request inside a policy has very little impact on the speed of that request, and the Poly team have been working on that over the last few years to make it even less of a performance issue. With regard to retry, there is one problem with it. When you send your request and it fails, you will retry immediately. When that comes back with a failure, it will retry immediately again. So if you're calling a system that's failing because it's already overloaded, you're not helping by hammering it with more requests. You're also making life much worse for yourself because you're opening up potentially more sockets, more threads, more memory in use. What would be better would be to give that remote system a chance to recover. And that's where the wait and retry policy comes in. When you make a request, if it fails, you pause and then you retry. If that one fails, you can pause a little longer and so on. And you can choose any algorithm you want to calculate the period between retries. This gives the remote system a chance to recover. For anyone familiar with networking protocols, Ethernet uses something like this when there are packet collisions. If you are making multiple simultaneous requests using the same wait and retry policy, they could all potentially back off and retry at the exact same time. And that's not good because you're going to have a burst of requests hitting the remote system at 2 seconds, at 6 seconds, at 14 seconds. So you can add a little jitter to that delay calculation function. So it helps randomize when the retries happen. Here's what a retry looks like. So I showed you a little earlier. It says handle HTTP response messages. And if it's anything other than a success code, retry 3 times. And then this is what a wait and retry looks like. Again, it's the same handles clause, but now it says retry up to 3 times. But here's a way of calculating the delay between the retries. And again, you can use any calculation you want. I mentioned reauthorization because it's a more interesting case. There's not much use in retrying the exact same request if you're getting an unauthorized error. Instead, what you do is you use the onRetry delegate as part of the policy. So the policy at a high level says if it's not a success code, you should retry. And then specifically within the retry, prior to executing the retry, this block is hit. And if the status code is unauthorized, you perform some custom reauthorization logic. That might be going out and getting a new JWT or a new cookie or whatever it happens to be. One drawback on this one is if you try to do this with a HttpClientFactory, it is more complicated. But I have some examples on my blog for that one. One thing that I've been asked at conferences was, can Poly be used for non-HTTP requests? And it can. You can pretty much use Poly when calling any method, whether or not it returns something. So here are a few examples. Here I'm checking the result coming back. That's an int. I'm checking if it's not 0 or if there was an exception, retry 3 times. And here I'm executing it. In these examples, you have to execute your code explicitly inside the policy because you're not using HttpClientFactory. A relatively straightforward example. I have a enum of type job status, and if the response is not valid, I'm performing a wait and retry. And with this one, I'm simply saying if an exception is thrown when I call this code, retry up to 3 times. So that's the retry and wait and retry policies. Another policy is the fallback policy. It's usually the last one that you would use when you're executing a request. So you might have a retry, and then outside it would be a fallback. You can return some sort of default value when everything else has failed. Fallback also supports a delegate that allows you to perform any action you want. So maybe you will page someone or restart a service or scale a system, something like that. And its code looks like this. In this case, I'm checking if the status code I got back was an internal server error or not. And I'm generating a whole new HTTP response message to return instead of what I was expecting to get from the endpoint I was calling. The next policy is a circuit breaker. So this is quite like the circuit breaker in your home, or in some countries, they're referred to as trip switches. It cuts the connection when a problem is detected. Circuit breaker has 3 states. The closed state is the normal operational state. Closed like an electrical circuit, current flows. In our case, requests flow. Open, no requests are flowing. And if a caller makes a request via something protected by a circuit breaker, they will get a broken circuit exception immediately, no delays. And then finally, there's a half open status. This is a sort of test status. When a real request is made and the circuit breaker is in half open, if the response comes back from the remote system as a success, the circuit breaker switches to closed. If not, it switches back to open. I'll show you all this in a state diagram in a moment. There are 2 kinds of circuit breaker, the original circuit breaker and an advanced circuit breaker. The original one will open if there are some number of consecutive failures. So 2 failures in a row, 3 failures in a row. The advanced circuit breaker opens if a percentage of failures occurs over time and there's a minimum throughput. And I'll show you 2 examples in a second. But to make things clear, the circuit breaker starts in a closed state. If there are problems, it transitions to open. After a period of time being open, it will transition to half open. If a request fails during half open, it transitions to open again, stays open for a period, moves back to half open, and then if that following request works, it moves back to closed. And again, just to hammer the point home, when the circuit breaker is open, it immediately returns exceptions. Again, not using up any resources on your application, not holding threads, not holding memory, not holding sockets. If my application is connected to multiple remote applications and each has multiple endpoints, a circuit breaker could be used to protect a single endpoint, a group of endpoints, or, unlikely the case, all outbound requests. I mentioned that there are 2 kinds of circuit breaker. This is the original one. It says if there are 2 consecutive errors, break the circuit for 60 seconds. On break, on reset, and on half open are delegates that you can use when the circuit breaks, when it's closing, and when it's in a half open state. You could use it for logging or other purposes. The advanced circuit breaker says if 50% of requests in a 30-second window with a minimum throughput of 7 requests have failed, so half the requests in a 30-second window have failed and you've had at least 7 requests, then break the circuit for 60 seconds. So this allows you to add a little more nuance to breaking your circuit. The circuit breaker I showed is fine if you have a single instance of an application, but if you have multiple instances, for the circuit breaker to function correctly, all the instances of your application need to share the state. How many times have you had a request that failed? And that's where something like Azure Durable Functions or Azure Durable Entity Functions is the answer. Poly has a new-ish library that allows you to use Azure Durable Entity Functions to store that state and distribute your circuit breaker across multiple instances of an application. Quick recap. The reactive strategies were retry, wait and retry, circuit breaker, and fallback. They respond to something that has already happened and try to help you recover from a problem. I mentioned that you can wrap requests, wrap policies. If you've got a HTTP request protected by a retry, around that, a retry policy, around that you can have a circuit breaker policy, and around that you can have a fallback. So there's nothing to stop you from nesting policies within each other to any degree you want. I mentioned that there's a thing called a policy registry, and this is effectively a dictionary where you can store policies or wrap policies, and it can be passed around your application with dependency injection or used with HttpClientFactory. And this one gets very interesting. HttpClientFactory uses the policy registry and a method to pick an appropriate policy and apply it to that request. You might choose a different policy depending on the HTTP verb or the endpoint the request is hitting. So for a get, you might use a retry. For a put, you might use a wait and retry. And for a post, you might want to use a no-op policy. But it's entirely up to you to pick the policy most suitable. I sometimes am asked about testing. And there are a few scenarios in which you want to test poly. So some people want to test their code as though no policy exists, to see the application running as though poly were not there. And you can swap in a no-op policy for a retry or a circuit breaker or for anything along the way. Another scenario is you might want to test how your application would behave when an exception from poly is thrown. So the broken circuit exception or a timeout rejected exception, what will your application do in response to that? And for that, you can use mocking. And more recently, there's a secondary repository or package that's been developed based on poly called Simi. It's a chaos engineering and fault injection tool. It lets you generate exceptions, alter results, delay requests, or perform pretty much any task up to dropping a database prior to making a request. And this will let you test your policies very, very well. On the proactive side, these are policies that monitor ongoing events and attempt to prevent problems from occurring, or they'll try to stabilize your system or potentially let it fail gracefully. Poly has 3 of these. The timeout. This lets you decide when to time out rather than some default imposed by the piece of code you're using. Caching allows you to store responses for a period. And then finally, bulkhead isolation. This one will protect your resources so one part of your application cannot bring down the whole application. With timeout, if a request goes unanswered, it will time out. Your choice is how it will time out. HTTP timeout, in the past, it used to take up to 100 seconds for a request to time out. So your process could be sitting there waiting, and anything that depends on it would also be waiting. So potentially threads, memories, sockets. Or you could use a poly timeout policy in which you specify how long a request will wait, and if no response is received within that period, poly throws a timeout rejected exception. You can, of course, wrap this policy inside a retry or any other policy. The timing out quickly also means that the application calling you doesn't waste resources waiting for a response. And in most scenarios, with a HTTP request, if you haven't gotten an answer within a second or two, you probably won't get one. It's a very, very simple policy. This one says the policy will wait 1 second. If you don't get a response, you will time out and throw an exception. The cache policy is a tricky one to demo or to explain in a short period. It's a policy that often isn't used by itself, but wrapped around other policies. You can use anything that gets stored in the cache in multiple places within your application, not just the part where you loaded information into that cache. You can potentially store a full HTTP response if you wanted to, but that's a slightly unusual case. Usually you want to store just business data. And it supports all the traditional on-cache get, miss, put, error, and whatever other methods you'd expect from a typical cache. Here are 2 cache policies. One is caching the whole HTTP response for 5 minutes. And the second one is caching, let's say, the business data, a catalog item, for 5 minutes. By default, the cache policy will use a relative time to live, but it also supports absolute time, sliding window, or result TTL. In the event that you're making a HTTP request and the header includes a response specifying how long something should remain in the cache, the result TTL can be used to set that time to the exact amount you got in the response. As I said, it's quite involved to show the code for it, so please take a look at my blog. I have 4 or 5 examples of using it. Here's what happens if your application can't handle all the requests it's receiving or trying to make. The whole thing will sink. Memory gets used up, threads and sockets will be held. But this could potentially have a downstream effect on applications because you're no longer responding to their requests. They're also going to hold on to threads. They're going to hold on to sockets and memory too. So you could have a cascading effect on other applications. The term comes from the nautical world, where bulkheads in ships were used to prevent flooding from going from one compartment to another. So the idea being your whole ship should not sink if one bulkhead is compromised. Same thing with your application. Here is a quick example of how you might end up in a scenario where bulkhead would help you. Your local system is making multiple fast requests to a remote system, but it's only getting 50% responses. After a while, you will have so many outstanding requests holding onto so much memory and sockets that your application will fail. Here's what a bulkhead looks like in Poly. It's made up of execution slots and queue slots. When you get requests in, they move to the execution slots. When they're full, subsequent requests will move to queue slots. Any more requests coming in will be rejected with an exception immediately. When an execution slot frees up, something will be moved from the queue slot into the execution slot, and you can now accept another request. This limits the amount of memory, processor, CPU, threads, everything that any part of your application can use. And for something so complicated, the policy is simple to write. It says 3 execution slots, 6 queue slots, and that's it. If we imagine that our application has 100% of resources available, using the bulkhead isolation will allow you to protect it from having all of those resources used by any particular part of the application. So you start with 100%, and then as the application runs, the bulkhead isolation policy will prevent all the resources from being consumed. This keeps your whole application stable. That is a quick whirlwind tour of Poly. If you want more information, please check out my Pluralsight course. My blog, I have quite a lot of examples on this and some on Simi. There's the active Poly Slack channel. GitHub is very active as well. And finally, there is a blog. Excuse me, a blog from the Poly team. Thank you very much for your time. John, I cannot hear you. It's not just me. Other people are saying it.
Oh my goodness.
There we
I've
go.
done this twice now. I'm just new to this whole thing. So we had a few questions on whether Poly is usable with Blazor, specifically WebAssembly.
I have not done so, but it's usable in anything that .NET runs on. I have not tried it in that case.
Great. Okay. Also had a question about gRPC, and it's usable. You said it's usable with anything, not just HTTP,
Yeah.
but should work fine with gRPC too, huh?
Any method you can call a Poly policy can be used to execute it. So a simple method that returns a string, a complicated method that calls out to a database, HTTP client, pretty much anything. I've tended to focus in my work on the HTTP side, but it works on anything.
Great. Okay. One last question is working with non-200 responses. So for instance, like a response that says, wants you to throttle or something like that.
I'm not quite sure I understand.
So if so not just a network exception, but if you get a response from the server, but the server has an API response that says,
yeah, you can specify
too many requests.
In your handles clause, you can check the status that comes back for anything you want. So in the event of a 3 something or a 4 something or a 5 something, you can have the behavior clause kick in. If that doesn't answer the question, the person can contact me directly on Twitter. My DMs are open and I'm very happy to discuss.
Awesome. Okay, that was amazing. Thanks a bunch. And yeah, if you've got questions that Brian wasn't able to get to, then head on over to Twitter and that would be great there.
Thank you very much.